welcome back. Alright, so we've seen why there's a limit. There has to be some limit. You can't make your windmill perfectly efficient and extract 100% of the kinetic energy from the flow. The question is, Betz's law says that it has to be the limit as to how much energy there could be extracted from the flow is this very weird number of 16/27. That is a very strange number. It happens to be 59.3%. Why? Why is it the strange number? Well, we're going to go back and think about this fraction here again that we had before. 16/27 is this ratio that I have over here on the right-hand side of the screen. It's the ratio of how much power the windmill removed to how much power was incident upwind from the, how much kinetic energy was incident upwind from the turbine. All right. Now, we need to kind of define some symbols here that will help us think this through. The blades of the windmill as they're turning are going to be sweeping through an area that the air is passing through, and we're going to call that area S. It's going to turn out that S is going to disappear, but we need it for thinking about our problem for a minute here. S will be this area that's swept out by the blades of the turbine here. And upwind from the flow, the air that is going to end up going through that area S is passing through an area we're going to call A1. 1 again being upwind, right? So some slice of air is what's going to pass through that turbine. Now we generally assume that A1 is going to be equal to that turbine, although under different conditions it wouldn't necessarily have to be, but it's kind of like this is the air that is fated to go back through the blades of that turbine. Meanwhile, downwind, the air will be passing through another area. Now, that area will be A2, 2 being our subscript, that means downwind, and as it happens, that's area that the air that flowed through the turbines will occupy once it goes through the turbine is generally greater than the area of the blades itself. The air will spread out after it passes through the turbine. Now, let me draw that to you a slightly different way here. So here's my turbine down there, just a little piece of turbine clip art there. And my flow, V1, is approaching the turbine. Before it gets to the turbine, that air that is fated to go through the turbine there is passing through an area we're going to call A1. The air goes through the turbine and slows down. See how my V2 arrows are smaller than my V1 arrows? And as it does, the air is going to spread out, passing through an area the size of A2. Alright, so we're going to pass through A1 at a velocity V1, and the air is going to pass through A2 at a velocity V2. In fact, that's an equation in meteorology. I couldn't come up, it only occurred to me a few minutes ago, I should have labeled it. A1 times V1 equals A2 minus A times V2. It's not Bernoulli's equation, it's not the Boussinesq equation. I can't think of the name of that equation, but meteorologists use it. It's the gap wind equation in meteorology. It explains any time a fluid has to pass through apertures of different sizes. It's why water speeds up when you send it through a nozzle. It's why, anyway, I can't think of the name of that equation right now, but it's there. A1 times V1 equals A2 times V2 is okay. As long as density doesn't change, that's true. Now, in general, because the flow is going to be slower on the downwind side, V2 will be smaller than V1. You can work through the math and show that in general A2 has to be bigger than A1. In fact, if it weren't, we'd have a problem here again. Let's say that flow didn't spread out and air passed through the area A1 before it got to the turbine at velocity 1, passed through the turbine, and then downwind it didn't spread out. A2 was the same size as A1, and V2 was, well, by that math, V2 would have to be the same as V1. But if V2 and V1 are the same, then kinetic energy upwind and kinetic energy downwind are the same. If the kinetic energy upwind and the kinetic energy downwind are the same, how much energy do we remove from that wind? 0. So this would be another example of a botched design of a twin turbine. This turbine also would produce no power at all. Okay. It would be useless. So we know in general A2 is going to have to be bigger. The air is going to spread out as it passes through after it passes through the turbine. And in fact, you can take a look at a picture of like a wind farm or something like that on a foggy day, or where they're using smoke to indicate how the air is flowing or something like that. And you can see how the flow, once it goes through the turbine, spreads out. This is in general a property of how wind turbines work. The question is, how much? How much should it spread out? Because, I mean, another way of asking that would be to say how much slower should V2 be than V1? Remember, because A2 and V2 are very related to each other. So we're basically saying, how do we make a wind turbine so that we slow down the wind and it spreads out in such a way that we get the most power as possible. I mean, we already know how to make a turbine that makes no power by not having the wind spread out at all. For that matter, we know another way to make a wind turbine that doesn't make any power. Have the wind slow down completely, down to 0 speed. So we could either have the wind speed downwind be 0, which that doesn't give us any power, or we could have the wind speed downwind from the turbine be the same as the wind speed upwind from the turbine, but that doesn't make any power either. So apparently there must be some wind speed along the way in which we do generate power. There has to be some downwind wind speed, V2, that we actually get power. In fact, there's got to be some wind speed downwind from the turbine where we get the most power. There must be some speed, V2, that is between 0 and V1 that is producing the most power. That is what we're looking for. That's what Betz's law is looking for. Now, if you've taken calculus, this sounds familiar. Calculus, one of the things we do with differentials and so on is we use them to find the maximum. We use a calculus that in such a way so that we can solve and figure out what the maximum, what is the value of V2 that produces the maximum amount of power. So we know there is some speed V2, I'm just using these 3 bullet points here that are cleverly made with turbines. So we know there is some speed V2 such that the turbine is creating the maximum amount of power it can. The maximum fraction of kinetic energy 1 is getting turned into power. Betz's law tells us that it has to be the V2 such that it makes 16/27 as much power as what was upwind, but why? Why is it that weird number? Alright, well let's figure this out. Now we could start with first principles like F equals ma, Newton's second law, which we're not going to do right now, but you can start with things like F equals ma and show that the power being produced by the turbine is equal to this ratio, where S was the cross-section of the turbine, rho is the density of air, the V that doesn't have any subscripts at all, that's actually hypothetically the velocity of the air passing through the turbine itself. In contrast to V1 and V2, which is the wind speed upwind and downwind from the turbine or whatever. Again, you could start from F equals ma and derive this. I actually did in my notes and then decided that that was not what was important in the presentation here. But you could get this equation here. This V is a hypothetical thing. There's no way to actually measure the speed of the wind actually in the turbine itself, but it can be proven that a reasonable approximation to this is that this V, the wind speed in the turbine itself, is just the average of the wind speed ahead and behind the turbine. Okay, turns out it can be shown that mathematically it turns out once the actual answer we're going to get with Betz's law, it doesn't matter what we put in here. Okay, but we're not doing that part of the proof, okay? We're just going to talk here about how this, if we plug in that velocity there, we make that substitution and you do some algebra, you get that, and then you get this nifty long thing that's above the little window I'm in right now. Alright, and this is all the power that is being produced by our turbine. Okay. It looks horrid. You'd be forgiven for thinking this looks horrid, but it actually isn't so bad because actually everything in here except V2 is a constant. You're not in control of what the density of the air is. Once the turbine is built, you are not in control of what S is. You're not in control of what V1, the wind speed up there from the turbine is. You're only in control of things like how the blades are pitched and so on, so that you can control V2, the speed downwind from the turbine. So actually, even though that looks like a giant mess, only thing that's a variable here is V2. We're going to actually plug those things in. By the way, I do want to interject here real quick here in this little black box here. With a bunch more algebra, you can rearrange this equation into this form. We're going to call that equation 1. Again, I don't care. We're not going to do the derivation of how we got from there to there. It's just a bunch more algebra. But we're going to need that form of the equation later in this process of understanding Betz's law. So kind of, stick a pin in that idea for a second here. Alright, so this is the power being produced, and it depends on the downstream wind speed, V2. Alright, so this is where calculus comes in. This is the kind of problem calculus is made to solve. Calculus tells us, it gives us a way of figuring out what is the speed V2 that maximizes the P. I mean, we know if V2 is equal to 0, the power is, there's no wind speed, downwind speed at all, we know that the power is going to be 0. If V2 is equal to V1, the wind speed upwind, we know that the power is going to be 0. Someplace between V2 equals 0 and V2 equals 1, there's a value of V2 that maximizes the power. Is that the pinching theorem? I forget. Some calculus equation, some theorem you learned in calculus tells you that this has to be true. I can't think of what, maximum value theorem or something like that. Whatever. I took calculus 25 years ago. I can't remember the word. Alright, so you could actually do that derivative. Again, if you're a survivor of calculus, you know that it's messy but doable. You make this derivative here. You're taking the derivative of the power with respect to the variable we want, v2. You do the error, you divide through by v1, you get this messy thing down here in the bottom. The actual doing the algebra, doing the calculus, I don't care about that right now. Okay, there'll be times when we care about it. Betz's law, I don't. So there's our equation. Now that looks messy, but again, keep in mind v2 is the only variable. v1 is actually a constant. It's something we measure from the wind. Well, this messy thing can actually be factored, or you could solve it actually using the quadratic equation, but if you did, you could factor it this way, and then, okay, well, it's a product of two things that are equal to 0. Either that first term is equal to 0 or that second term is equal to 0. Well, v2 minus v1 over 3, if that's going to be equal to 0, the only way that's going to happen is if v2 equals v1 divided by 3. If v2 is 1/3, if the velocity downwind from the turbine is equal to 1/3 of the velocity upwind, the math works out, and the right-hand side becomes equal to 0. Oh, our wind speed has to change then, so that the downwind speed of the wind is 1/3 of the wind speed upwind. By the way, that other one is a possibility too. That second term there with 3 over v1 squared. All right, that is a weird non-physical solution. It turns out that mathematically you could also produce the most power if that one were equal to 0. But in order for that to work, v2 has to actually be in the opposite direction as v1. Well, turbines don't really work that way. Okay. There is apparently some solution in which your turbine would be maximally efficient if the downwind for the turbine was actually in the opposite direction and also heading back towards the turbine, but that's not physical. That's not the way turbines really work. So we've now solved for v2. The speed downwind from the turbine that produces the most power is if the velocity downwind from the turbine is 1/3 the velocity upwind from the turbine. Okay, well you can plug that ratio, v2 to v1 equals 1/3, back into that thing that we called equation 1. Okay, feel free to just chunk it in there and you do the math and it's, oh my gosh, all these horrible fractions and looking for common denominators and all that kind of crap. And you get the thing down there in the bottom, that the maximum power being produced happens when this is true. The maximum power being produced, rather, is this. Okay, that's that bottom equation there. Well, okay, so the left-hand side, P max, the maximum power that the turbine can produce, is equal to this thing I have in the red box here, 1/2 rho times S, the area of the turbine, times velocity upstream cubed. Hey, wait a minute, that's the kinetic energy of the wind upstream from the turbine. Okay, but not all of it. This fraction, 16/27, or 60% roughly. So the maximum power you can produce from the turbine is roughly 60% times the kinetic energy of the wind upstream. And it does not matter what kind of turbine you make. I mean, I don't even know the names for all these different, I googled unusual turbines or something like that and just got a bunch of images here. It doesn't matter whether it's designed vertically or horizontally or on a rooftop or have 2 blades or 50 blades. It doesn't matter. You are limited to approximately 60% of the kinetic energy of the wind at any given time, no matter how you adjust your turbine. Now, notice though, that is an important detail here. That is just telling us how much power can be captured from the wind. This is not telling us like how much electricity the turbine can produce or something like that, because that's going to depend on the engineering and going on inside of it, the dynamos and things like that, and the generators and so on. This is just like, literally as in the kinetic energy of the shaft of the turbine. We are not yet anywhere near like thinking about like how we're going to produce electricity from that. But all you can harvest from the flow itself is that 60%, or capture is the better word. All you can capture from the flow itself is 60% of the kinetic energy. What a strange little bit of physics. Now let's answer a couple quick questions about what we just saw, and then we'll be done with this lecture. Question 3. As the flow goes through a turbine, we assume that it's A, velocity, B, kinetic energy, or C, density is constant. Hey, somewhere in there I made an assumption that I didn't actually say the words. Did you catch what happened here? Which of these things is constant as the air passes through the turbine? Alright, make a choice from those 3 options. Let's see if you noticed that, and get a little feedback before you move on to question 4.